With the release of Godot 4.3 comes the awesome new feature called the Compositor, which allows you to inject additional logic into the rendering pipeline at various stages to create post-processing effects. Gone are the days where we have to create a full-screen color rect node, or set a quad mesh as child of the camera for a full-screen effect. Compositor uses Compute Shader, which is a special kind of shader that is targeted towards general-purpose programming. In simple words, unlike Fragment or Vertex Shader that has a fixed purpose, Compute Shaders are more flexible because they don't have any fixed purpose. They also have very little going on behind the scenes. The code you write is what GPU will execute and very little else, which is why Compute Shaders are a very useful tool to offload heavy calculations onto the GPU. Compute Shaders are an advanced topic and requires a GLSL file where you will write instructions you want GPU to execute, and you will also need a script file from where you will execute the compute shader, pass the data to the GPU, and get back the results. Of course, you can quickly get a template from the official docs containing the minimal code required for a compute shader, and docs or any other tutorial will call that code a boilerplate code. But in this tutorial, I will create those two files step by step from the scratch. Let's go. First, let's create a GLSL file. I will call it postprocess.glsl. Now, Godot cannot edit GLSL files directly, so you have to use an external editor. I will just use Notepad++. Now, I've installed GLSL language integration, which highlights the syntax and have basic autocompletion from super awesome Daniel Shazers. I will put the repo link in the description if you're interested. Alright, now in GLSL file, I will go #compute. This will tell the GPU that this is a compute shader code. Then version 450. This line specifies the targeted OpenGL version 4.50. Then here, I will define invocations in workgroups. In other words, define the compute space. Layout, local size x equals 16, local size y equals 16, and local size z equals 1 in. This line will define local invocations on x, y, and z workgroups, and I will define the number of workgroups from the script in a bit. By doing that, I will define the compute space in a memory for my shader to execute. Workgroups and invocations are an advanced topic, so it is a bit hard to explain. I will put a link in the description where you can read more. Official documentation says to think of them as a gigantic nested for loops, which in my opinion is a bit confusing, so let's try to understand it with an example. Let's say I have dispatched my compute shader with workgroup set 221. Think of them as a 3D grid. So I will get 4 workgroups. And now let's assume I have defined local invocations as 441. So within a single workgroup, I will have 16 cores or threads where my shader instructions will execute, and these threads will execute in parallel or simultaneously. Now these workgroups will execute independently from each other, and the order will be determined by the GPU. So GPU could execute this workgroup first, then this one, and so on. Now you might think that why this is important. Let's say I have a 4K display and I want to create a full screen effect, so my shader would run for over 8 million pixels, and my GPU or any other consumer grade GPU won't have enough cores to perform 8 million parallel computations. So we need to divide the workload into smaller chunks. Now in this example, I only have 64 total threads. The GPU is powerful enough to execute them in parallel, so for this case, all of this will run in parallel. So keep that in mind. Then in the shader, I need a screen texture to read from and write to in order to apply the post-processing effect. So I will go uniform image 2D screen texture. And I also need to define the layout qualifier, layout, then the image format, RGBA, 16-bit float precision, then binding equals 0, and setID equals 0. And from the script, I have to match this binding and set ID. The layout qualifier will tell the GPU where to look for the image in the memory space. Then I will also pass some custom data as well from the script. So to catch that, uniform params for parameters, and this will be a struct, so curly braces, and then define the variable, so p. Here the first thing I need is screen size, so vec2 screen size. Then I have to define the layout qualifier here as well, so layout push constant, then std430. Push constant will tell that this is the push constant block, and this std430 is the set of layout rules that specifies what type of data this block can hold. std430 was introduced in OpenGL version 4.30, hence 430. Shocker. So this means the block can hold scalar values, vectors, arrays, and matrices. Alright, then void main. This is the entry point of our shader. Do not capitalize the M here. Then here let's grab the pixel ID, ivec2, integer vector2, pixel equals ivec2 of GL global invocation ID.xy. So the workgroups and local invocations have a global ID, and I'm reading that here. And this pixel can go from 00 up to the screen size. Now I have this screen size. Let's grab it in a variable. vec2 size equals p dot screen size. Of course I can just use p dot screen size, but this is just for convenience. Then I will check if pixel.x is greater than equals size.x, or pixel.y is greater than equals size.y. If so, simply return. So this line makes sure that I won't access anything outside my compute space. Now let's read from our screen texture. So vec4 color equals image load, then pass screen texture, then I will pass the pixel coordinate. And the screen texture is an image 2D because we have to write back to that screen texture. So image store and screen texture, and pass the pixel coordinates and write the color. And now here I can modify the color before I write it back. Let's just invert the colors for now. So color.rgb equals 1 minus color.rgb. And this is our shader file done. Let's create a script to run this file. In Godot, create a new script. I will call it postprocess as well. In the script, I will give a class name postprocess. And it extends from Compositor effect class. Now you might find it a bit odd the way I wrote this, but in my opinion, this is more readable. Then I will use tool keyword, so the script can execute in the editor as well. Now a heads up first, I've worked with strictly typed languages my entire life, so here I will also define types for everything, because it is easier for me to comprehend. Okay, so here I go var rd of type rendering device. This is just the abstract class to work with low-level graphics API. Then I need a shader reference, so var shader of type RID. RID is the class that uniquely identifies the resource at low level. Then I need a compute pipeline reference as well, so var pipeline of type RID. Then let's first override the notification method. This method will execute when our script receives any notification signals. There are 3 types of signals the script can receive: post initialize, pre-delete, and extension reload. I can check what notification I received using the what parameter. If what equals notification pre-delete, This notification will be received when the object is about to be deleted. So here basically I'm checking is the script instance is about to be destroyed. If so, I want to free these resources from the memory. Rendering server free RIT shader. This will free the shader from the memory. I have to do this to avoid memory leaks. Now notice that I'm only freeing the shader and not the pipeline because pipeline will be released along with the shader. But right now the shader is already null, so if I were to free it directly like this will throw an exception. To prevent that, I will also check if shader is valid. And that is all for our notification method. Now let me create a custom method to initialize my compute shader. Function initialize compute shader. And this will return nothing, so void. And for now, let's just keep it empty. Now I need to call this method. I will do that in init method. This is the entry point of my script. I will call initialize compute shader method here, but I don't want to run it on CPU, so I will call it onto the render thread. Rendering server dot call on render thread initialize compute shader. Now let's define initialize compute shader. First, let's just initialize rendering device, so rd equals rendering server dot get rendering device. Now this method could return null, so let's check if not rd, meaning if rd is null, then simply return. Then here let's just load our GLSL shader, so var GLSL file of type rd shader file equals load, then give path of the GLSL file. Then I will initialize the shader reference from that file, so shader equals rd.shader create from spurv. This method will create a shader instance from spurv or spur5 intermediate code. Think of it as assembly instruction. Then here I need to pass spurv code, but I only have GLSL file. But rd shader file class has nice method to get spurv code. Get spurv. Then I also need to initialize pipeline reference, so pipeline equals rd.compute pipeline create from our shader. And that is all for our initialize compute shader method. Now let's override render callback method. This method is the bread and butter for our post-process compute shader. Here I will define the workgroups, pass our data to the GPU, execute the compute shader, and get back the results. And the render callback method will be called on render thread every frame. Here let's first check if not rd. If rendering device is null, simply return. If not, let's get reference to our render buffer. Var scene buffers of type render scene buffers rd equals render data dot get render scene buffers. Then let's also check if not scene buffers. If it is null, return. If not, let's get the size of the frame buffer or resolution. Var size of type vector2i equals scene buffers dot get internal size. Then let's check if any dimension is 0. If size.x equals 0 or size.y equals 0, return. If not, let's define x and y workgroups. Var x groups of type int equals size.x, and same thing for y workgroups. And workgroups cannot be 0, hence I check for the dimension here. So right now I've defined the workgroups for every pixels, but remember that in the shader I've also set the local invocations 16. So I will divide both of them by 16. Then I also need to send resolution or screen size to my shader via push constants. So var push constants, and the type will be 32-bit float array. So packed float 32 array equals new packed float 32 array. Then I will just append my data here. Push constants dot append size dot x and size dot y. And in the shader, I've defined it as vector 2. But here I have float array, so I need to add them one by one, and I have to be careful about the order as well. Then let's do a for loop for view in scene buffers.getViewCount. This is for just in case if we are doing stereo rendering, VR. Then I need to pass the screen texture to the shader, so let's grab it. Var screen texture of type RID equals. Then I can get the screen texture from the scene buffers, so scene buffers dot get color layer from current view. Okay, I have the screen texture. I need to pass it as a uniform, so var uniform of type RD uniform equals RD uniform dot new. Then I need to define a uniform type, so uniform dot uniform type equals image, because I've defined it as image 2D in my shader. Then I also have to set the binding, and I have to match it to my shader as well, so uniform dot binding equals 0. Then I need to add the image, uniform dot add ID screen texture. Now based on this uniform reference, I need to create a uniform set to pass it to the shader. Var image uniform set of type RID equals uniform set cache RD dot get cache. So to pass the shader reference, then pass the set ID, and I need to match it with the shader, so 0, and pass uniform as array. Okay, now I have the uniform set and push constant array. Let's create a compute list. Var compute list of type integer equals rd dot compute list begin. This is just some command to talk to graphics API. Then I need to bind the render pipeline, so rd dot compute bind compute pipeline. Then pass in compute list and our pipeline. Then I need to bind the uniform set, rd.compute bind uniform set, pass our compute list, our uniform set, image uniform set, then set id. Once again I need to match it with shaders, so 0. Then I need to pass my push constants, so rd.compute list set push constant, pass in the compute list. Then here I need to pass the push constant array as byte array. So simply push constants dot 2 byte array. Then I need to specify the memory size of the array in bytes. One element will be of 4 bytes, so push constants dot size multiply 4. Then I will dispatch the compute list on X, Y, and Z workgroups. rd.compute list dispatch, pass in the compute list, X groups, Y groups, and 1 in Z workgroups. This will submit the compute list for processing on the GPU. Then at the end, I have to tell that okay, that is all, so rd.compute list end. And notice that I'm not reading the data back because in the shader, I'm already overwriting the screen texture. In the scene, you have to create the world environment node. Then in the inspector, you will have this brand new compositor slot. Select the new compositor. Here we have compositor effects. Hit add element. Then here you will have the custom effect, in this case, new post process. Select it, and I have errors. The compute pipeline requires 16 bytes of push constant data, supplied 8. So here in the push constants array, I'm only adding 2 elements, so 4 plus 4 equals 8 bytes. I need to pass 2 more, so push constant.append, let's just pass 0, and do that one more time to meet the 16 bytes requirement. Then let's test again. And I have full screen effect with negative colors. Now notice that at the bottom the effect is not properly applied. That's probably because of this integer division. So let's simply add 1 on both workgroups. And the issue is gone. Yay! Now here in the inspector I have this effect callback type slot, which is the inject point on which stage I want to inject the post-processing logic. Pre-opaque means before opaque objects have been rendered. Post-opaque means after opaque objects has been rendered. Post-sky means after the skybox is rendered. Pre-transparent means before transparent objects has been rendered. And post-transparent means after entire scene is rendered. So let's say I don't want to apply the post-process on this cube. I will just change the cube material to transparent and set the effect callback type pre-transparent. So now the cube is unaffected by the effect because the transparent objects are now getting rendered after the post-process effect. Awesome! Now let's see how to pass a sampler 2D to our shader. So for example, let's try to visualize the depth texture. For that, in the shader, let's define a sampler 2D uniform sampler 2D depth texture. Then I have to set the layout qualifier, so layout binding equals 0 and set ID equals 1. Set ID needs to be different for each uniform. Then in the push constant block, let's pass inverse projection matrix third columns W component and fourth columns W components. Float inverse projection 2W and float inverse projection 3W. Then to sample the texture, I need UVs, which I don't have, but I can calculate it. So vec2 UV equals current pixel coordinate divided by size. Then here float depth equals texture. Then the texture to sample is depth texture with UV and take any single channel. Then let's quickly get the depth in view space and linearize it. So float linear depth equals 1 divided by depth multiply p dot inverse projection matrix 2W plus p dot inverse projection matrix 3W. Then let's clamp it between 0 to 1. So linear depth equals clamp linear depth 0 and 1. And I only want to visualize depth up to, let's say, 50 meters. So divide by 50 here. And if you don't know what is going on here, you are missing out. Go check out my scene depth video. Then here color.rgb equals vec3 of linear depth. Here let's first pass inverse projection matrix component as push constants. But how can I get inverse projection matrix? I can get it from scene data, so let's grab that first. Var scene data of type render scene data rd equals render data dot get render scene data. Then let's also check if it is null or not. So simply append the if statement or not scene data. Then here var inverse projection matrix of type projection equals scene data dot get cam projection. But this is projection matrix, so let's inverse it. Then in push constants array, pass inverse projection matrix third columns W component and inverse projection matrix fourth columns W component. Now I need a depth texture, so var depth texture of type RID equals scene buffers dot get depth layer of current view. Then I also need to create a uniform. I can recycle this uniform, so copy all this and paste it here. Remove the declaration part. Then uniform type will be sampler with texture. I have to match the binding, but it is 0 in the shader, so let's keep it that way. Then instead of screen texture, pass depth texture. Then I need to create a uniform set, var depth uniform set of type RID equals uniform set cache RD dot get cache, pass shader. Then I need to match the set ID, so pass 1, then pass uniform as array. Then I also need to bind this uniform set, so rd.computeList bind uniform set, pass compute list, then depth uniform set, and match the set ID with shader 1. And I have errors. Sampler texture should provide 2 IDs referencing a sampler and then a texture. IDs provided 1. So in this uniform, I only set the texture. I also need to add a sampler first. So let's quickly create a linear sampler. Var sampler state of type RD sampler state equals RD sampler state new. Then sampler state dot min filter equals sampler filter linear minification filter. Do the same for magnification filter, so mag filter. Then var linear sampler of type RID equals RD dot sampler create, pass our sampler state. Then let's add it to the uniform before our texture, so uniform dot add ID linear sampler. And now let's check again. And I can see depth. Awesome! Now I have a challenge for you. Try to replicate my full screen outline effect using Compositor. It would be a nice exercise. And I will not link these 2 files on Patreon for now. And you might hate me for that, but my intention is to force you to write these files at least once so you can wrap your mind around how compute shaders work. Once you learn how to wield the power of compute shaders, you can pull wonders regarding performance. And now if you have any questions, post them in the comments, and if you're new here, feel free to smash that subscribe button for more videos like this. That's it from me, and I will see you in the next one.